In this video, we are going to master U-Substitution. We will start with a basic problem, and by the end, we will solve a definite integral that requires changing the limits. So let's begin. First, we need to recall the logic behind here. So suppose that we have a integral out here of the form f of g of x times g prime of x dx. And we suppose here that this gx is differentiable. There. Now what we do in the substitution, U-substitution, is that we let a variable for this thing out here. So let's say we let u be equal to g of x. If u is equal to g of x, then du must be equal to the derivative of this g prime of x times dx, since dx came from this one. Then if you have this, then this means that we can rewrite the given into the integral, or the antiderivative if you want, of f of u du. Essentially, we replace the g of x here with u, and then the g prime of x dx here with du. So that is the logic for this one. So we will apply this logic in the following examples. Let's first move this out here. And yeah, start with the first one. For this first one, we will have the following. So we have here the integral of x squared times the quantity x cubed plus 1 raised to 10 dx. So here, to apply the u substitution, we first choose what we will decide upon to be u. So here you can, the natural thing to do is just to trial and error. Like choose, check what happens, and so on. In here, observe that if we choose u to be x squared, then its derivative will be 2x. But 2x is nowhere to be found here. So that won't really work, and that won't cancel this out. What we can choose instead is x cubed plus 1. Because notice that if we take its derivative, x squared will appear out there. So let's do that one. So let u be equal to x cubed plus 1. If u is equal to x cubed plus 1, then we will have here du to be equal to 3x squared dx. And once you have this one, then all we have to do is to match what we have here to the given. So to do that one, we can rewrite the given as x cubed plus 1 raised to 10 out here times x squared dx. Since there's no 3 out here, unlike here, what we can do here is we can rewrite this one as du over 3 equal to x squared dx. There. Essentially what I did is that I divided 3 both sides, so the 3 moved here, no more 3. So once we have this, we can now apply our U-substitution. This thing here will just become u raised to 10, and then the x squared dx out here will just become du over 3. So we'll have here du, and then the 1 over 3, I can just move it outside since it's just a constant. Then once you have this one is now easy to integrate. This will just be equal to 1/3 of u raised to 11 over 11 plus c. So that is by the power rule in anti-differentiation or integration. Oops. Once you have that one, then just take note that when we start with the in terms of x, we must also end in terms of x. So we just replace the u out here with the corresponding function of x. So the answer for this one will just be 1 over 33 times x cubed plus 1 raised to 11 plus c. This is the final answer for this first problem. Okay, so there you go. Take note here that what do you call this? Oh, there. Another way to solve this is to expand this x cubed plus 1 raised to 10, and then you won't need to apply the substitution rule out there. But that is kind of hard since you'll need to recall how to expand when you raise something to 10. So that one is a bit complicated. This one is more compact and clean. Good. Let's move on to the second one. We have the following. Okay. So for this next one, you might get worried because there is an ln x, but actually in integration, when you see an ln x, you should be grateful, because if ever you choose that as your u, its derivative is just 1 over x, so it's pretty simple. And that is actually what we will choose as u. So we can let here u be equal to ln x, because like I said earlier, then the du would just be 1 over x, and of course dx. This matches perfectly with what we have, since we have an over x here in the denominator. So once we have that, just to emphasize it more clearly, we can write this one as ln x cubed times 1 over x dx. Basically, I just moved away the or split this expression out here into 2, just to emphasize the substitution that we will do. Okay, so applying the U-substitution, we will obtain here u cubed, and then 1 over x dx is exactly du out here. So we'll have here du. and this one is just easy to integrate. This will just be equal to u raised to 4 all over 4 plus c, and then since we started with x, we must end with x. So we'll have here ln of x raised to 4. Since we chose u to be ln x, plus c. This is the final answer for this problem. Yep. So as you can see, U-substitution makes our life easier. Let's move on to the third one. For the third one, we will have the following integral. There. So we have here the integral of e raised to 1 over x all over x squared dx. For this one, you may try choosing different u's. One may try choosing x squared, but if you choose x squared, then you will have x. If you choose, let's do this correctly. If we choose u to be equal to x squared, then du will be 2x dx. This isn't ideal since there really isn't x out here. Okay, so that won't really be a good choice, and you can keep on trying, trial and error, and what you'll see is that a good choice is choosing 1 over x or e raised to 1 over x, but I'll do the 1 over x one. So just to emphasize why is that, take note that we can write this one as the integral of e raised to x raised to negative 1 times x raised to negative 2 dx. So this is just by laws of exponents. 1 over x is just x raised to negative 1. The x squared being in the denominator is just equal to x raised to negative 2. There. So we can now apply U-substitution. So like I said earlier, we'll choose u to be equal to x raised to negative 1. By power rule, we will have negative x raised to negative 2 dx. Okay. And then just to match what we have out here, since there is no negative out here, we can just rewrite this one as negative du equal to x squared dx. Essentially, I just moved the negative to the other side, or in other words, I multiplied negative both sides to obtain negative here, and then negative times negative will be positive out here. Okay, good. So wait a second, so let me just move this out here, and I guess this out here. Okay, good. Okay, never mind, let's just move this out here, go back with this, and since there isn't quite some space out here due to this, let me just write the next part out here. So by U-substitution, this will just be equal to e raised to u, then this one will be the du. And then don't forget that there must be a negative out here because of this. So that is a common error of students, that they forget the negative out here since it's not quite evident, unlike constants that you move around. So you just take note of that one. And then from here, the integral of an exponential, specifically e raised to a variable, is just itself, right? Since the derivative of exponential of e is just itself, so the antiderivative would just be itself. There you go. And then again, going back to x, since u here is equal to x raised to -1, then we'll have here e raised to negative e raised to x raised to -1 plus c. But just to match what we were given originally, let me write this as negative e raised to 1 over x plus c. This is the answer for this side. Yep. So like I said earlier, an alternative here is that you can let u be equal to e raised to 1 over x, and I think you'll get the same thing. Okay, good. Let's move on to the fourth one. For this fourth one, we have the following. So for this fourth one, we have the integral of x times square root of x minus 3 dx. One might think that this is just straightforward, but there's actually a hidden trick to be used out here. So let's decide again on what to choose to be u. If you choose u to be x, then it's just like a pointless substitution. Suppose we choose u to be equal to x, du is equal to dx. So essentially, you'll just replace the x's here with u. So nothing good would really happen out there. So the suggestion here is to choose the other one, this one, x minus 3. You could choose square root of x minus 3, you can try that one, but the derivative there would be complicated. So x minus 3 is the most natural choice out here. So we let u be equal to x minus 3. If this is the case, du is going to be equal to dx. Right? So essentially, this one will become square root of, oops, sorry about that. This one will become the square root of u. I am pertaining to this part out here. It will become square root of u. And then dx here will just be du. Now the problem here is that we haven't really applied any change to x out here. Okay. We can't pertain x, we can't just write x out here, since when you apply a substitution, every variable must change. So from x, all of that must become u. You can't have x and u in one integrand. So what do we do about that? Well, we have here a relationship connecting the two. Okay, so take note that out here, so let me use a different ball pen or colored pen, probably this red here. Take note that by this relationship, we actually know that x is equal to u plus 3. Why is that? Well, you just move -3 to the other side, or add 3 both sides to obtain that one. Now we have a relationship, or we have an expression equal to x, which is a function of u, this one. So that is what we will use to substitute x out here. Okay, so let's maybe use this one. Not really a fan of this type of red. We'll fix that next time. this one. Nah, it's too dark. Okay, so going back, now that we have this, we just need to simplify this. So observe that we can actually write square root of u as u raised to 1/2 du. From there, this is now easier to manipulate. So you just distribute this inside the expression. That will give you u raised to 3/2 plus 3u raised to 1/2 du. Let me just fix this one. I'm not liking the equal sign out here. Let's just write this. It's like that. Okay, I think that's better. And let's just fix the spacing. Yeah, apologies for this. I like things to look nicer, I think. Okay, I think that's better. And then from here, we just apply the power rule in anti-differentiation. So we will have to call this, we'll have here u raised to 5/2 all over 5/2 plus 3 u raised to 3/2 all over 3/2 plus c. And then again, we go back to x. So first, take note that if we have 5/2 out here, if you have a fraction in the denominator, technically it would like flip. So this thing here would just be equal to, or more to be precise, this 2/5, or just 5/2 out here will just become 2/5. Okay, u raised to 5/2, but u again is just x minus 3. So this one will become x minus 3 raised to 5/2 plus this 3/2 out here would result to 2/3. So the 3's here will cancel. We'll be left with 2 u raised to 3/2, but u is just x minus 3. So we'll have here x minus 3 raised to 3/2 plus, yeah, this is the answer for this problem. So that is for number 4. Okay, just one last. We now move to the last problem. If you're liking this video so far, make sure to like and subscribe to this channel. That would really help for me. Yeah. Okay, so for the 5th item, we'll have here the following. Okay, so we have here the definite integral from 0 to pi/4 of tangent cube x times secant squared x dx. Okay, so this time we are now ready to deal with a definite integral involving U-substitution. Okay, so for this one, again, our first step is to choose the u, corresponding u that we need. For u here, we probably have 2 good choices, either secant x or tangent x. If you use secant x, suppose we choose this one, du will become secant x tangent x dx. The secant x would be dealt with, but the tangent here is a problem since we only have one tangent out here and it's not cube. Okay, so I guess you could do some more steps out there to deal with that one, But a better choice is to choose tangent x. So like I said earlier, U-substitution is more of a trial and error, but through practice it becomes pretty easy to spot which is the right choice. So if we let u to be equal to tangent x, du will be equal to secant squared x dx, perfectly eliminating this problem, and then the u would deal with this one. Okay. Now the key here in definite integrals is that if you apply U-substitution, you must also replace the limits of integration with that rhyme. And why is that? Well, this limits of integration are in terms of x. So essentially this one is x equal to pi over 4, then we have x equal to 0. So our goal is to replace that to be in terms of u. So by that, we will have here x equal to pi over 4. If that would go to u, then we'll have here, we will use this relationship. So we will have here tangent of pi over 4. And then just recall from your basic knowledge that this is just equal to 1. Okay, tangent pi over 4, or in degrees that is tangent 45 degrees. Other than that, we have here x equal to 0. So x equal to 0. On the other hand, we will have here u equal to tangent of 0. And then here again, just recall that tangent of 0 would be equal to 0. There. Basically sine 0 over cosine 0. Yep. And then so once all of that was already set up, we will now apply the following changes. For the limits of integration, from 0 to pi over 4, we will now have 0 to 1. So we'll have here 0 to 1. And then tangent cube x out here will become u cube. And then secant squared x dx would be replaced by du. Good. So I hope you're still able to follow what we have out here. And then from here, this is just easy to integrate again, or anti-differentiate. So we'll have here u raised to 4 over 4. And then by the second fundamental theorem of calculus, we'll have here u equal to 0 and u equal to 1. What this means is that we just evaluate the given. So we'll have here 1 raised to 4 all over 4 minus 0 raised to 4 all over 4. Okay? So essentially what the second fundamental theorem of calculus is telling us is that you just evaluate this antiderivative from this minus this. This one will just be 0. 1 raised to 4 is just 1. So we will be left with 1 over 4 out here. And this one is the answer for the problem. Good. So that completes what we have. So this is a list of all the problems that we have. Yeah, maybe I could rearrange this so that things would fit better. So let's move the 2 out here. The 3 out, and see here. The 4 out, out here, and then the 5 out here. I think that's a good spacing. So this is what we had in this video. Okay, we had a basic substitution, substitution involving ln's, substitution involving e's, with a negative emphasis on the negative part out here. Substitution that involves a certain trick. And then a definite integral involving a substitution of trigonometric stuff. Obtaining this. Yeah, so I hope you enjoyed that one. If you survived all 5 problems, then good job. I believe that you already have quite a good understanding of how the substitution technique works. If you want a clean PDF of these solutions to study offline, the link is in the description down below. It's for free, but if you want to donate, then that would really help support the channel. So yeah, I hope you enjoyed that one, and see you in the next video.